creo que a las 3. Y
El anuncio dice a las 11.
no, es que acabo de hablar con Gustavo. Yo creo que lo vamos a cambiar a las 3 y él va a hablar mucho de convección también, una aplicación, un experimento que hicimos en 2003 sobre el monzón, la región monzonal aquí en México. Y yo creo que salió bien la tesis de él. Entonces, les recomiendo que vayan. Preguntas. Si alguien lo hace llorar, pero dinero aquí. Okay, then.
Do you remind them about their homework?
Yes. Y nada más ayer creo que 2 o 3 personas entregaron su tarea. ¿Cuál fue la tarea? Hacer una pregunta de lo que sea, de lo que han visto. El más importante para nosotros es que nos digan exactamente por qué están, bueno, qué es lo que les interesó del curso, porque es posible que hagamos esto como cada año, no necesariamente con Ben, pero bueno, a mí me gustaría que siguiera viniendo, ¿no? Pero podría ser con otros colegas en convección, en metodología tropical. ¿Okay? Entonces, sí, por favor, ¿qué es lo que les llamó la atención? Y una pregunta nos ayudaría mucho.
All right, thanks a lot, Dave. Welcome back to day number 4. It's good to see those of you here toughening it out. One more day after today, and then we're done. And as Dave mentioned, we kind of switched up the schedule of things today, so that's actually a good thing because then we'll finish off the week with Dave. So we'll go out with a bang.
There you go.
Yeah. So what I'd like to do today is, there was a little bit I didn't cover from yesterday's lecture, which I'd just like to touch on. In part it's something that's of interest to me, and we'll try to bring the conversation back to what the main thrust of yesterday was, which is kind of the theory of the coupling or the interaction between convection and the large scales. So I think what I'll talk about is kind of another example of that. And then I want to turn to looking at the representation of convection in models, in particular, how we represent convection in coarse resolution models. You might call them global climate models, essentially the models that, if you're familiar with the coupled model intercomparison project, CMIP, that would be sort of the category of model that we're talking about. So how we represent convection in general, tropical convection in specifically in those models, look a little bit at what the models actually produce in terms of convection, and focus on things like errors and biases that exist within the models. And I kind of added a little section here on sort of tools for evaluating models with respect to how they perform regarding convection. One kind of example of that, it kind of follows from a point that Kathleen made on Tuesday about the kinds of diagnostics that she and her colleagues are developing, are kind of meant to be tools for model evaluation. So this is kind of another example of that. So, oops. First slide here I just wanted to show because it's nice to look at a picture of clouds. This is actually a picture that I took flying over the Southwest Pacific. If you've ever flown over the Pacific, you realize just how big it is. This is like a small corner of the Pacific, and it's like the size of the Gulf of Mexico or something. So the Pacific is a big place. And I wanted to show this picture in particular because the example, the piece that was left over from yesterday's talk is kind of in this region, close by at least to where I took this picture. And so let me just get to it. So in particular, what I've become interested in part, or initially interested in as a result of the sort of work that I was doing with the convective margins that I talked about yesterday, is this feature in the southern hemisphere Pacific, known as the South Pacific Convergent Zone. And, you know, again, we kind of mentioned this feature like the Intertropical Convergence Zone, which affects, you know, central Mesoamerica. The SPCZ is different. You know, as you can see, the ITCZ is a very narrow, zonally elongated feature. The SPCZ is diagonally tilted. I think this is an image. This is a image of rainfall from TRIM, I believe, for the month of January. So in the month of January is kind of when the SPCZ is most well developed. And you can see in that month, you know, it extends all the way from the deep tropics in the western Pacific warm pool, halfway across the Pacific to, you know, around 30 south. This is interesting for many reasons. It's interesting in part because it kind of spans the entire tropics. You know, we go all the way from the equator to mid-latitudes, or at least the subtropical latitudes in the southern hemisphere. The kind of, and I'll talk a little bit more about this, the sort of structure that this feature has is of interest for various reasons. It's also of interest because, like in the northern hemisphere, there's a storm track in the southern hemisphere, so essentially you have a zone of baroclinicity in the southern hemisphere, and so you have these disturbances that propagate along just like we have in the northern hemisphere, and those interact with the convection in the SPCZ. And so it's kind of an interesting place in the sense that it's a locus or a center of interaction between things happening in the lower latitudes and things happening in the higher latitudes. So I began initially working on this in the context of the sort of convective margins model that I was talking about yesterday. And since then, we've kind of expanded, you know, the kinds of things that we're doing in this area. So I just listed a few of them here. And I'll talk about a couple of these as we go on. So just to kind of orient you schematically to the geography and climate of the South Pacific, Australia, the maritime continent, the Philippines, up here is the southern coast of China. We have the South Pacific Convergent Zone. You can see in this kind of schematic, it's even kind of cut off here. It might even extend a little bit further. It exists essentially completely over the ocean. We have a comparable feature to the South Pacific Convergence Zone in the Atlantic called the South Atlantic Convergence Zone. That South Atlantic Convergence Zone would be anchored over South America, but this is, you know, sort of completely oceanic. You can see some of the other climate features, you know, the trade winds, the warm pool, the Intertropical Convergence Zone. And, you know, it's an interesting place in a sense. So my kind of northern hemisphere perspective on this, you know, I'm one of a handful of people on our side of the planet that actually works on this. The Australians are very interested in it for obvious reasons. So as kind of I think there's a lot of work to be done in the southern hemisphere. So if you're kind of looking for a new place to go and break new territory, there's really a lot we don't really understand about the meteorology and climate in the southern hemisphere. So, you know, just the kind of plug to go south of the equator. Why is the South Pacific Convergence Zone important? Well, you can see there's quite a large number of islands in the South Pacific. So you have places like Fiji, Samoa, the Cook Islands. All of these island nations in the South Pacific are influenced, their climate is influenced to a large extent by the South Pacific Convergence Zone. So, you know, it's kind of drawn here in its sort of mean position, but the South Pacific Convergence Zone actually moves back and forth. And so you can have a place like Fiji, if it's sitting underneath the South Pacific Convergence Zone, it can be very wet. If the South Pacific Convergence Zone is not over top of Fiji, it's very dry. And, you know, despite being islands surrounded by water, it's water that you can't drink, most of these islands depend on rainfall as their source of water. Fiji has a few rivers and lakes, but a lot of the smaller islands have no groundwater of any sort. So they rely on rainfall almost exclusively for drinking water and other needs. Here's just some context of flooding in Fiji back in April 2012. Actually, I think it was in 2012 that Fiji had a double whammy. They had extensive flooding in January, and then just a few months later had equally extensive flooding. These kind of flooding events, as they happen in other places, are because of synoptic scale features. I think in this case it was a monsoon depression that just kind of parked itself over Fiji for a few days and they got lots of rain. But those synoptic scale features in the South Pacific, to a large extent, the characteristics of them depend on the South Pacific convergence zone, or they're related to it. So in particular, along this kind of southern boundary of the South Pacific convergence zone is where you tend to see a region of tropical cyclogenesis. So, this is one of the sort of tropical cyclone regions in the southern hemisphere. So that's an active area of interest to understand how tropical cyclogenesis interacts with these larger scale features. To give you some other context about the sort of longer scale or lower frequency variability of the South Pacific convergence zone, there's well-known relationships between the El Nino Southern Oscillation and the position of the SPCZ. So in particular, during El Nino events, when the Central and Eastern Pacific is anomalously warm, the convection in the South Pacific convergence zone tends to shift toward the northeast, toward the equator, migrates toward the warmer water in the Eastern Pacific. During La Nina, it tends to shift in the opposite direction. It's maybe a little bit more subtle than that. I'll try to talk a little bit more about that. But there are these this paper by Wenju Kai and colleagues appeared, I think, in Nature in 2012, kind of talking about very extreme, what they called zonal SPCZ events. So this plot shows the results of a principal component analysis that Kai and colleagues performed, where they basically were looking at the rainfall patterns using principal component or empirical orthogonal function analysis and identifying the leading modes of variability, interannual variability in this part of the world. And the interesting thing that they noticed when they plotted the second principal component against the first is this very sort of nonlinear relationship. Now, of course, for those of you who know about principal component analysis, by definition, by the way principal components are constructed, these have to be orthogonal in a linear least squares sense, but you can still have a kind of higher order structure that you see here. So these events, 97, 98, 82, 83, and 91, 92, kind of stick out as being very unusual. And what Kai and colleagues have hypothesized is that when you have the right kind of ENSO conditions, so it's, 97, 98, and 82, 83, those were intense El Nino events. 91, 92, not so intense, but it was kind of this weird, in the early 90s, there was kind of a persistent El Nino. So it seems to be some combination of the strength of El Nino, but also the spatial distribution of the sea surface temperature anomalies that kind of give you this tendency to create these so-called zonal SPCZ events. And in a sense, what happens, you can't really see it maybe so much from the principal component itself, but the line here would kind of indicate the axis of the SPCZ for these three events. And so you essentially have a collapse of the SPCZ onto the equator, or you can think of it, there's a single, instead of having an ITCZ and an SPCZ, you just have a single zonal band of convection. And so you might imagine if you have a state in the Pacific like this, given the interactions between convection and the large scale, that this might have very significant impacts on climate. And certainly from the point of view of these little islands that sit down here, this is a very bad thing because the whole region then gets dry if the SPCZ collapses. This study also generated a lot of interest because Kai and colleagues kind of looked forward in the future and asked, in the context of CMIP5 models, is it more likely that we'll see this kind of configuration of rainfall in the Pacific? And they actually suggested maybe that's true, that this type of zonal SPCZ event will become more common in the future. Although since they published that, there's been some pushback that maybe that's not actually the case. But still, it's kind of an interesting situation nonetheless. What I think is, I haven't actually looked yet for this year, but the current El Nino event, the Godzilla, looks a lot like these El Nino events. And so if I had to speculate, I would say that, we're likely to see this kind of configuration this year. We should have the data soon enough to kind of, make that assessment. So I've been kind of talking in some general terms about why the SPCZ is important, why we're kind of interested in studying it. So but it be a bit more specific, what kind of drew me to the SPCZ in the first place is how sort of fundamental questions about how the South Pacific Convergence Zone is generated and maintained, and what factors lead to it having its kind of distinct spatial characteristics. In other words, why is it diagonally oriented and not zonal like the ITCZ? Despite it being a very large feature, if you look at a weather map or if you look at a map of climatological rainfall for January, it's sort of the largest continuous convecting feature on Earth. Continuous in the sense of, a monthly mean spatial structure. And yet we still really don't know why it's generated or how it's maintained. There was a nice review paper in 2007 by Takahashi and Battisti, or it was part of a study that they did where they kind of reviewed the literature on the SPCZ, and they actually distinguished two sort of broad paradigms to kind of understand its structure and its characteristics, and they called them Western control and Eastern control. Western control, as the name implies, suggests that the source, what actually causes the SPCZ, if you will, happens in the western part of the Pacific Basin. So in particular, the kind of theories or studies that sort of support this idea of Western control kind of focus on the role of convective heating over the Western Pacific warm pool and these sort of associated wave dynamics that sort of large body of warm water close to the equator is going to have. So studies like the Linzen and Nigam work by George Kalatis. I think George is coming here to visit, so maybe he'll talk about these kind of wave dynamics. Adrian Matthews, some more recent work by Matt Widlansky. I got interested in this coming at it from the Eastern control side, so suggesting that we should look to the east to try to understand what's going on. And in particular, the idea here is that we can understand the SPCZ primarily in terms of the advection of low moist static energy, low-level moist static energy that's low, i.e. cool and dry. Those air masses coming from the southeast tropical Pacific. If you remember the kind of overview I did of the Pacific in the context of ENSO, is that we have this strong SST gradient that exists zonally in the Pacific with cool sea surface temperature in the east, warm in the west. And so the sort of moist static energy of the low-level air masses, is lower in the east than it is in the west. And going back to this, sorry for toggling back, but you essentially have trade winds that are blowing from east to west, or maybe southeast to northwest, that are kind of bringing low-level air, low-level, low moist static energy air from east to west. So more about sort of the advection of air masses. And I would say too that maybe the kind of Western, the way I've maybe thought more about this is that Western control is kind of upper, sort of emphasizing what's happening in the upper levels with the wave dynamics, whereas Eastern control is more about the, advection at low levels. And there's been other, so I'll show some results from this paper that we did in 2008, but that was, the Eastern control was sort of Takahashi and Battisti's paper. They configured a really simple model. It's actually quite elegant, where they basically, what they were basically interested in is, why do we, and maybe I'll go back here, their sort of perspective was to focus more on why this sort of dry area exists in the first place. And so what they did was they kind of set up a model here, sort of coupled ocean atmosphere model, but very simplified, to try to create, to try to understand the conditions that lead to the formation of this dry region. And part of what they emphasized is that you have the Andes Mountains here, and that the Andes Mountains are essentially topographically forcing subsidence over this part of the Pacific. Now we see a similar kind of dry, I think maybe the counter argument to that is you see a similar dry zone exist over the Atlantic. And there certainly is some topography in Africa, but it's not the Andes. So maybe the topographic forcing isn't so important. And then there's also, of course, the role of the ocean dynamics. Right. So I should have mentioned in their model they didn't have ocean dynamics. They were just essentially thinking of this as a thermodynamic problem.
Yeah, but you have the cold water from the cold.
Right. So that's what Dave said, is that you do have ocean dynamics here. So I'm not saying. That's not to suggest the ocean dynamics aren't important. I think the ocean dynamics are absolutely important. Also, sort of in the context of the ocean dynamics, is that this region is characterized by low-level marine stratus clouds, which are very extensive, kind of preventing, in a sense, the clouds sort of prevent the system from warming up. So I think it's this complex mix of things. But still, the idea is to emphasize, to try to understand this in terms of its relationship to this. Oops, I'm going the wrong direction. So, okay, so this is sort of in what I've sort of have been discussing here is sort of in the realm of theory, but turning to more practical considerations maybe of modeling, it turns out that this region, really the whole of the Pacific is characterized by a number of well-known biases in climate simulation, including things like the double ITCZ, the fact that if you look at, and I'll actually show some results on this later, but if you look at the configuration of deep convection in the Eastern Pacific, you'll remember from our little survey of sort of the large-scale distribution of rainfall in the tropics that we should see a single ITCZ north of the equator in the Eastern Pacific. Many coupled models have a tendency to produce two ITCZs, so one both in the northern hemisphere where it should be, and one in the southern hemisphere. Now, I would mention here, if you actually look closely at the climatology of observed rainfall, there's an appearance of a double ITCZ, a weak one, but there is some appearance of a double ITCZ in the months of March and April. So there may be some real tendency in that part of the Pacific to create a double ITCZ, but the models want to have double ITCZ there sort of all the time. So there's that bias. There's biases sort of on the in terms of the simulation of the sea surface temperature field in the Eastern Pacific, giving rise to a too cold tongue. So this is the cold tongue problem, the fact that the water there is maybe colder than it should be. That cold water gets advected to the west, and I'll show a few results that are kind of relevant to how that impacts rainfall. Focusing more on the SPCZ, when we look at model simulations, the SPCZ is often simulated as much too zonal, so it doesn't have the right diagonal tilt. And the convection in the SPCZ often penetrates too far to the east into that sort of dry zone. And I'll come back to those things later. So I got interested in this, as I said, kind of wanting to apply this kind of convective margins kind of idea, simple sort of mass balance, simple sort of moisture balance model to try to understand the variability in the SPCZ. So we sort of focused on this sort of eastern edge of the SPCZ, where you have this kind of strong trade wind inflow that's kind of coming in from the southeast. And essentially what we did was set up a simple kind of composite analysis. So I mentioned composite analysis yesterday as a sort of data analysis technique. It's just, it's really just a conditional average. So we chose a kind of index to do the compositing with respect to. In particular, we looked at the strength of the zonal winds through this little box. We kept it, of course, the winds have a meridional component that actually turns out to be important, but to keep things simple, we just focused on the zonal component. And we constructed conditional averages based on whether the zonal wind there is anomalously weak. So anomalously weak corresponds to relaxed trade winds. The trade winds are not as strong. But because the trade winds are blowing from the mean wind there is from east to west, anomalously weak actually corresponds to a positive anomaly in the zonal wind. And then conversely, anomalously strong trade winds or negative anomalies in terms of the actual zonal wind value. So we used the average winds over that box, and then we just averaged other climate fields based on weather whether those anomalies are greater than or less than +1 standard deviation or -1 standard deviation. And so what I'm showing in the top panel, and I apologize, I don't really have didn't put the mean climate on here to sort of orient you, but the axis of the SPCZ would sort of, the mean SPCZ would kind of be through here. Okay, so what I'm showing in the top panel is two fields, of course, the wind field, 925 millibar winds, so kind of focusing again on the low levels, thinking in terms of low moist static energy air advection. And then the 850 millibar moisture field from NCEP. We actually used, I think, if I remember correctly, we used column water vapor as well from satellites, basically show the same thing, that you essentially have under conditions when the trade winds relax relative to conditions when the trade winds are strong. Of course, you see the direction of the winds for that difference is from west to east, as you expect. But you see a moistening of the 850 millibar level, kind of along the northeast edge of the SPCZ. In terms of the rainfall, you see during the phase when the trade winds are relaxed that the convection is actually supported further to the east than when the trade winds are strong. So we sort of interpreted this as, kind of pushing the SPCZ back and forth. And I should mention here that we kind of set up this analysis to focus on the synoptic scale variation. So there's a well-known tendency, as I mentioned, for El Nino conditions. An El Nino would be associated with an SPCZ maybe more like this, La Nina with an SPCZ more like this. But we controlled for that by kind of filtering out strong El Nino and La Nina events. So in sort of synoptic timescales, you kind of see this tendency for the SPCZ to shift back and forth.
Sorry.
Yep.
On that one, I guess like your analysis is based on the inside that yellow box, right? And from here I cannot see them. I don't have my glasses, but
Yeah.
like the strength of the velocity, like the velocity vectors, is it about the same over the areas where it's white and the areas where it's blue? You notice a big difference between those two?
I'm not sure I understand the question.
He's asking if, like in the blue area,
Here?
the wind vectors are the same size as in the white area.
They might be a little stronger.
Is that what you want?
Yeah, and also like what I wanted to ask, if they are a little stronger, did you carry an analysis on the weakness of the wind based on this? If the wind gets weaker or stronger in areas where there's no, I guess that's precipitable water or something?
Oh, sorry, this is specific humidity at 850, but we did the same thing on precipitable water. You essentially see the same signature, so it kind of suggests that, to the extent we can trust this as, a reanalysis product, that the precipitable water variability is kind of controlled by in this region is controlled by the low-level moisture.
Do you want to repeat the question?
Well, if I remember the question, if you do the same sort of analysis with precipitable water, do you get the same result? And the answer is yes. But your question is actually a good one because, of course, when you look at this, you sort of very clearly see that this is part of a cyclonic circulation, right? Remember, you're in the southern hemisphere, so your idea of cyclonic is opposite of what it is here in the northern hemisphere. So this is cyclonic circulation. Also point out, too, that this, so actually I can't quite remember, I think if I did this correctly, the places that are white shaded here maybe are not significant. Maybe I didn't actually do the significance. But I know in a version of this figure where I certainly did the significance, that this kind of wave-like structure that you see, and even these negative anomalies up here, that those seem to be robust. So it does suggest, again, our notion here was to focus sort of on the low levels, kind of in this region, but that's part of a broader structure, which, because it has this wave-like pattern, kind of suggests that, maybe the source of this is really, upstream of this part, and that we're kind of seeing, well, maybe I'll get there. So this is, to kind of go back to this kind of convective margins way of thinking, to look at longitudinal cross sections, so kind of throwing out the two-dimensional geometry for the moment, looking at the zonal wind, the column water vapor, and the precipitation. So for the red line here is that would correspond to the strong trade winds. The blue line corresponds to the weak trade winds. So when you have stronger than normal trade winds, you see a reduction in column water vapor, or associated with the strong trade winds is reduced column water vapor along the margin. When you have weaker trade winds, you have enhanced. You have precipitation, again, we have this kind of shift or this extension of the edge of the SPCZ off to the east when we have the weakened trade winds. Now, trade winds relax, moisture increases, the margin shifts. Oops, I actually took the arrows off here. This was supposed to have arrows to kind of get at the question of what's causing what. And I'll actually come back to this later. Our sort of notion when we kind of set up this analysis was to think about, the trade winds relax somehow. The relaxing of the trade winds basically allows the moisture here to increase. You have less dry air advection when the trade winds are weakened because there's a mean moisture gradient across here. Less dry air advection kind of bringing in dry air here. So, the moisture values aren't as low. And because you have higher column water vapor, that sort of thinking, at the time we weren't maybe thinking so much about it in the context of these kind of transition to strong convection statistics, but with higher column water vapor being able to support precipitation versus the case when we have lower column water vapor. But the causality could actually go in the opposite direction. You could have something that perturbs the convection. Perturbing convection, perturbing the moisture field kind of go together, but that precipitation drives the change in the trade winds. So it's an interesting question, right, is who's driving who in terms of the low-level winds versus the convection. And I'll actually come back to that. But I first just wanted to go through, again, the kind of simple, in the spirit of the simple calculations that we wanted to do with this kind of convective margins model, to kind of extend it into this domain. The details here really aren't so important other than to say that we can kind of work out what we did yesterday in terms of looking at the moisture profile along some inflow trajectory in terms of what controls how the moisture varies along that inflow trajectory. So you kind of see factors that are similar to what we talked about yesterday, like you have these related to the sort of vertical structure of the dry static energy, this related to the vertical structure of the moisture, radiative heating at the top of the atmosphere. Here, because we're over the ocean, we have an evaporation contribution. So you can look at how, for example, the analysis I ended with yesterday was to say what happens if you perturb one of these terms, how does the moisture or the precipitation change? You could do the same thing here. So what would happen if you increased clear sky radiative heating and so on and so forth? We get this length, just like we had with the model yesterday. You have a length scale. This is a slightly different length scale than what we had yesterday because we actually have a sort of contribution here from this model kind of has a Betz and Miller type convection scheme in it, and you kind of get this convective adjustment time scale as part of the length scale.
But that tau is the wasters.
No, this is, tau here is a convective adjustment time scale. Yeah, I don't think I stated that anywhere, but the precipitation is kind of in this Betz and Miller form. Again, where we're sort of switching temperature and moisture, we can actually do that in this model. And so it's basically a relaxation of something that's related to CAPE over some time scale tau sub c. And similarly, so that's the moisture field. Maybe more interesting is the precipitation field. So precipitation you can just get from this relationship here. So you get this form for the precipitation field. And what we can do with that then is we can kind of set up a kind of two-dimensional model. This two-dimensional model was kind of meant to mimic the conditions in this part of the Pacific. So we specify the moisture along this boundary, and then basically this thing here, if we generalize it to 2 dimensions, it allows us to fill in the moisture field and also the precipitation field. So these line contours are the moisture field, and the green back here is the precipitation. And we have to assume what the moisture distribution is along this direction and this direction. Essentially what we're assuming here is that this is the driest point in the domain, because if we look at the observations, we have a mean gradient in the moisture from dry to wet as you move toward the equator up into the ITCZ. And as you move zonally from the eastern Pacific to the west, you also have an increase in moisture along that boundary. So it's maybe not too surprising that if you impose a low-level wind that's basically advecting dry air off the boundaries, that it's going to create this dry sort of wedge in that part of the domain. But what we can do with it then, because it's a kind of simple diagnostic model, we could ask what happens if we change certain parameters in the model just to try to understand what's going on. So a kind of simple one to look at is this. Remember from what I was discussing yesterday that we have this sort of convective threshold that kind of comes out of the Betz and Miller convection scheme. So if you reduce the value of that convective threshold, that means an air mass needs to be less moist in order to convect. And so if QC is reduced, as you expect, you see the precipitation occupies more of the domain, or this sort of dry wedge is kind of reduced in its extent. But then we can also kind of do the perturbation problem. We can do the perturbation problem by saying, okay, we impose a wind field, but let's now perturb the wind field. We did something very simple. We just added Gaussian noise, a sort of constant Gaussian noise to the wind vectors to kind of mimic the effect of strengthening or weakening the trade winds. And then you can kind of do sort of the similar composite difference that we did with these observations. And, maybe not surprisingly, you kind of see when the trade winds are relaxed, you kind of have a moistening of this part of the domain, and you get then the increase in convection along. You basically, the convection, if the trade winds are weaker, you'd have the convection kind of occurring further to the east.
What are those contours?
These contours are specific humidity. They're not quite scaled for specific humidity, but it's essentially moisture.
And how do you know where your weekends the wind?
Because we're doing a composite difference. So what we do is this is a uniform wind field. We just impose a set of, you could think of it like a time series of Gaussian perturbations on that wind field.
But those Gaussian perturbations are uniform over the.
Right, that's correct.
So then how?
Because
So
the arrows are either longer or shorter.
Okay.
So, yeah, I see what you're saying. I don't have a wind field plotted on here because it's uniform, right? The difference between the positive and negative phase is uniform everywhere.
Yeah, well, I would guess like if you impose some white noise, you could actually perturb positively or negatively. But you just only allow the perturbations to be on one direction? Or?
No, they were both directions. The idea here was just to say, okay, we have some model, simple model, lots of caveats. We can put in what we know as the forcing. We're going to force the convection with the winds.
Yep.
And the idea was to show that you get something it's not implausible to say that, you can have this sort of shift in the edge of the SPCZ by imposing a reasonable value. The perturbations that we chose here were sort of reasonable values over sort of, over sort of the domain where we kind of expect these fluctuations are happening. One of the other illustrations of this was to say, okay, we know in models that there are certain uncertain parameters. So in this model, we can think about this convective threshold as a potential uncertain parameter. So we could say, what would happen to the variability? This is sort of an illustration of the variability in this model. What would happen to the variability if we changed one of these uncertain parameters? And the idea was simply to illustrate that the flavor of the variability, by reducing QC, you kind of shift, where this moistening and precipitation shift occur, because you've changed the mean, it's maybe simple, you've changed the mean state of the model, so the perturbations relative to the mean state look different here than what they do here, because it's a different mean state. And so this was to sort of illustrate the point that by looking at models, of course, we can evaluate biases in the mean states of the models, but also looking at things like biases in the variance or the variability relative to a mean state, and maybe then trying to draw connections between variations that we see in, say, the mean versus variations in the variability. And I'll come back to this point later, because I think there's this sort of way of thinking about looking at biases across different measures of precipitation kind of simultaneously and trying to link them together that I think it's potentially instructive or potentially tells us important things about why the models are behaving the way that they do. So I just wanted to come back to a point, maybe to follow up on something that we were, with respect to the question, that, okay, we have this, in the model that I just showed, we kind of outline the direction of causality. We know we've imposed the wind perturbation. And sort of by design of that model, the convection doesn't really feed back onto the winds. So maybe in that sense, it's a little bit artificial. But to just kind of look at that in a little bit more detail, and I'm just going to make a few comments on it. So think about the relationship between sea surface temperature and precipitation. So here's a map of NOAA extended sea surface temperature data, DJF. So you see the distribution of sea surface temperature, warm sea surface temperatures in the west, cool sea surface temperatures in the east, and then here's the map of precipitation. So sort of comparing them side by side, and just, let's focus on what's happening over the ocean, not over the land. Where you have the warm sea surface temperature, you tend to see the intense rainfall. So we see that in the SPCZ, in the ITCZ. So you kind of see, over here, the ITCZ kind of lines up with this maximum. The Atlantic ITCZ kind of lines up with the maximum. And if you just do a scatter plot, people have done these things for a long time. You can see that as the mean sea surface temperature increases, the precipitation increases. It has a, sort of nonlinear functional form, but people interpret this in terms of the simple thermodynamic argument that where you have the warm sea surface temperature, the atmosphere, above it tends to be moister and less stable. And so, it kind of makes sense at that level that as you warm sea surface temperature, you increase precipitation. But let's think now about the relationship among sea surface temperature, precipitation, and then kind of factor in the role of winds. And it turns out there are essentially two paradigms that have emerged about how, well, in particular winds and precipitation, how those two things should go together. So the first one, and this is kind of, if you want to read more about this kind of, these two paradigms, this 2006 paper by Adam Sobel and David Nealon, in the introduction, they have a really nice discussion of the two. But the first one is what they refer to as deep tropospheric thermodynamic control. And essentially, for this kind of paradigm, SST determines the vertical profiles of temperature and moisture, which determine precipitation and convective heating, and it's the convective heating in turn that determines the winds. So in a sense, what we've really been focusing on in this course, the topics that we've talked about, like convective quasi-equilibrium, WTG, the kind of QTCM model that I outlined yesterday, in a way these sort of align with this paradigm or this way of thinking. This paradigm isn't without its challenges, and so if you think back, kind of a sort of concrete example of this, in the model QTCM1 that I showed at the end of yesterday, you remember that model has a really hard time simulating narrow features like the intertropical convergence zone. So it seems like some aspects of tropical precipitation might be consistent with this kind of thermodynamic control paradigm, but other aspects, maybe like the ITCZ, aren't quite so consistent. And so the sort of opposite paradigm to this is what Sobel and Nealon call ABL dynamic control, atmospheric boundary layer. And essentially in the ABL dynamic control idea, you have the sea surface temperature. So again, we're sort of assuming the sea surface temperature in either of these is given. But here the sea surface temperature determines the low-level winds through pressure gradients. So basically, you have low surface pressure coincident with warm water, high surface pressure coincident with cold water. That sets up a pressure gradient. Pressure gradients drive winds. Winds drive moisture convergence, and the moisture convergence feeds precipitation. So probably the most well-known example of this sort of ABL dynamic control mechanism is this paper by Lindzen and Nigam in 1987, where they basically outlined this argument that you have surface fluxes determining ABL temperature. The ABL temperature determines surface pressure, kind of directly from hydrostatic balance. The thing about this kind of ABL dynamic control is that the moist physics and the radiation are largely irrelevant for determining the winds, except maybe to the extent that, they contribute to setting the SST in the first place. So where do you find warm or cold water in the first place? But, in a way, it kind of puts the control on things at low levels with respect to, setting up gradients and so on and so forth. Now, it turns out when you look kind of at either of these paradigms in nature, it can be hard to actually tell them apart. The first paradigm, the deep thermodynamic control, would sort of think about causality in terms of convection driving the winds, whereas the second one, winds drive convection. But they're quite difficult to tease apart because in reality, it's more like this. Convection drives winds, but winds also drive convection. And when you have this kind of thing where you say, well, on the one hand, I have convection driving winds, and on the other hand, I have winds driving convection, but the direction can actually go both ways, that's sort of a characteristic of a feedback process. And so, this sort of idea of this sort of dual directionality, that you can have convection, in fact, driving winds, but winds can then drive convection, this is sometimes referred to as the convection convergence or the convection circulation feedback. So we imagine somehow you perturb convection in some way in the tropics. That perturbation to convection, let's say you increase the convection, that increased convection is associated with ascend and low-level convergence, so that starts driving the winds. The winds that are converging can bring moisture into the convection zone that can cause the convection to go up. And so you can get this sort of virtuous feedback where you have, a positive feedback where one drives the other. So I kind of put this up here because, I think in terms of understanding tropical convection, we really have to think carefully about this kind of convection convergence feedback. And part of why I mention this is, it's very common for people in studying precipitation processes that, it's tempting to construct a budget. You say, I have a precipitation perturbation. I want to look at how that precipitation perturbation relates to advection, convergence, evaporation. Usually if you do that kind of budgeting for the tropics, what you find is that a perturbation in precipitation is balanced by a perturbation in moisture convergence. Because of this convection convergence feedback, that balance might obtain just as a result of the feedback, but not actually tell you about what caused things in the first place. And so that's maybe one of the nice things about the kind of modeling. I mean, maybe not as simple as the model that I showed, because that was more of a toy model for illustrative purposes, but that running, carefully designing model simulations, and again with caveats about how much you trust models, which we'll talk about, that you can maybe design experiments that allow you to kind of look into this. So I just wanted to follow up then on what I talked about with this quasi-equilibrium tropical circulation model. So I mentioned at the outset when I started talking about them that they're actually a family of models. We can think about QTCMs. The first one, QTCM1, had a single basis function, this temperature projection that we talked about yesterday, had a single vertical basis function. But the model, the framework itself is general. You can do that projection for an arbitrary number of modes. So that was done back in the early 2000s, and then, no one ever really followed up to any great extent trying to put in, well, maybe they did, but, there wasn't really follow-up. There was some sort of follow-up where people said, well, it might be interesting to decouple free tropospheric moisture from boundary layer moisture. So Roel Neggers kind of did that in the mid-2000s, gave the moisture part a second degree of freedom. But in that same Sobel and Nealon paper, where they were kind of thinking about this convection convergence feedback, basically what they said was, well, in the original QTCM1 version, it's really set up with this kind of deep tropospheric thermodynamic control in mind. Because there was no sort of explicit boundary layer, or the boundary layer wasn't free to kind of do this low-level convergence, that model basically didn't have the physics that are sort of implicit in this ABL dynamic control. And so what they argued is, well, maybe let's redesign this kind of QTCM framework, but instead of doing it, in a general way, let's think about specifically splitting it between some free troposphere and some fixed boundary layer. So, this is obviously the boundary layer moves with time, but in this kind of simple framework to just kind of decouple what's happening in the lower, 100 millibars from what happens up above. So for QTCM2, the specific set of basis functions were implemented essentially by inserting this fixed depth but prognostic atmospheric boundary layer beneath the free troposphere. And so again, the kind of theory or the motivation for doing this is to enable both the sort of thermodynamic control and the ABL control paradigms to be operational in this particular model. And the model, I think, as I kind of hope I showed yesterday, has been successful in many applications. So this was sort of intended to kind of leverage on the success of the model, but allow it to do other things that it couldn't do before. So again, the methodology, we have impose these basis functions in the boundary layer. You make the assumption that the boundary layer is well mixed, so not the temperature, but the dry static energy or the potential temperature is constant with height, the moisture is constant with height, and the winds are also constant with height. And then in the free troposphere, essentially take the same basis functions that we had before, but just kind of cut them off at 900 millibars. So QTCM2, the implementation that was done by Adam and David was in an axisymmetric model. So what they were really hoping in the axisymmetric model, what they were actually able to show, is that by putting in this kind of boundary layer and allowing this Linz-Niggam type mechanism, that they could actually get much sharper convection features. So the problem that I alluded to with the QTCM1 is that things like the ITCZ, very narrow convection zones, it just really can't simulate, or it simulates very weakly. But by adding this kind of boundary layer mechanism, the Linz-Niggam mechanism, they were actually able to show that the ITCZ could get much stronger in that version of the model. So that was an encouraging thing, And this wasn't without some expectation, because in the literature of the ITCZ, of course there's a deep convective heating mode that happens in the ITCZ, but there's also a shallow convective, or a shallow mode, or a shallow circulation kind of within the ITCZ that the first version of the model just wasn't capable of doing. Yeah.
What is an axisymmetric?
Oh, sorry, axisymmetric. It's zonally symmetric. So there's no longitudinal. Yeah, sorry about that. Yep.
In the Linz-Niggam, what's the surface flux? Is that something? I'm just kind of thinking a little bit like Karaman and kind of wishy thing. Increase the winds, increase surface flux.
Right. So what's the surface? So the question was, what's the surface flux in the Linz-Niggam? It's the surface energy and moisture fluxes, sensible and latent heat flux.
Something like a wish kind of instability, or
I'm not sure. I don't know in Linz and Niggam if they actually talked about wishy or not, but I think it's related.
okay. So I just think it's a little bit hard. You got convergence, but it's also hard to separate out from increased surface flux if you're increasing the winds with convection.
Right. So, yeah, when I was kind of going through this sort of, or I guess here, I'm sort of assuming the SST is fixed, right? But obviously, like with this thing, for example, particularly in terms of the feedback, if the wind speed changes, might increase the surface exchange. That might cool the ocean surface, and, things can get complicated then because of the coupling between the ocean and the atmosphere. So this was sort of short-circuiting that. Oops. So the idea, which was sort of supported